Pleasure to introduce David here. David is going to talk about graphs, matrices, and some property testing kind of things. David, I leave the stage here.
Okay. Thank you very much for the great opportunity to give the presentation here at Google. My name is David Ingerman. I am from Seattle, Washington. And I am going to talk about data representation by graphs, matrices, formulas, and continued fractions, and inverse problems for Laplace operator. So what I would like to show that graphs and matrices can be used to represent a lot of very diverse information in a uniform way. And then it can be used for data analysis. And also a lot of transformations of data can be represented by graphs and matrices. And then I will talk about one problem in particular in more detail. So first I would like to talk about three different, very briefly, about three projects that I work on in Microsoft Research. And this is collaborative work with Lonnie Wu, Steve Altshuler, Edward Junk, and Greg Ridgway. So these three projects have resulted in 6 United States patents. And I would like to show you just several different areas where the matrices and graphs appear. And then I would like to talk about one project in much more detail, about inverse problems for a graph for a Laplace operator. This is a problem where one tries to observe a graph or random walk on a graph only at a boundary and would like to figure out how the graph looks like inside. And I'll talk about it later. There are a lot of problems in mathematics, for example, that can be converted to this problem. So even if it sounds not very familiar, you will see, I hope, that many problems can be converted to this one. So a graph is a set of nodes connected by the links, and it can be directed or not directed, and it can be annotated, it can be semantic graph. And so something like this. So a matrix usually associated to a graph is a matrix which is n by n, where n is the number of nodes in the graph. And the matrices I will talk about today mostly, they have the following structure. If there is a connection from node I to node j, then the entry in the matrix is non-zero. So this matrix M is not zero if there is a link, and zero if there is no link. And such a matrix can be called adjacency matrix or Laplace matrix for a graph. So I would like to show just very first three projects, and especially because they are connected to the internet problems and web propagation data on the web, for example. I would like to show talk very briefly about this project and just show how graphs and matrices can be used in very different situations. So first project is the following. Suppose you would like to advertise a certain web page to users. Then what we can do, we can look at the historic data, how people were looking at other web pages, and then to infer from this information so-called influential rumor mongers. We can see we can look at the order in which people are looking at the other web pages, and from it deduce who is talking to who, and who influences other person decision to look or not to look at the web page. So suppose you would like to advertise a web page C. Let's first look how people are looking at the web pages A and B, for example. So suppose we have the following data, that we have web page A and web page B, and we know that user 3 at the day 1, so let's say this is day 1, day 2, day 3, day 4, day 5. Suppose we look at the order in which the people are looking at the web pages. 4, 3, 2, 3, 5. Then we can sort of deduce that maybe if a person 1 was looking at the web page after person 3, maybe the person 3 was talking to the person 1, and he saw first the web page and then recommended it to the person 1. And the same thing here. Maybe people 3 and 5 were influenced by the suggestion of person 2 to look at the web page. So here we can represent the data by the following graph. We can represent the users that are looking at the web pages by a graph where the entities will represent users. And from this, we can deduce that maybe person 1 is talking to person 2, and 2 is talking to person 5, and 2 is talking to person 3, and 4 is talking to person 3. So this was one of the projects, is to, given the historic data of how people are looking at web pages A and B, try to figure out the graph of influence, who is talking to who. And then, once we know this graph, we can choose the influential rumor mongers, the people who talk to many people, and rather than just randomly give an advertisement, give it, for example, to person 1, and then we can be sure that in 2 days, everybody, 2, 3, and 5 will know. At the same time, if we do not know this graph, then we have to tell to everybody, for example. Then we can miss. We can, for example, give redundant information. Tell to person 3 and to person 2. At the same time, this is very natural for people to recommend web pages to each other. So it's better to give a person 2, and then the person 3 will know from the person 2. So once the graph is learned, then we can very efficiently spread the advertisement, for example. And what we learn from this process, if there are a lot of connections, if people talk to each other a lot, then it doesn't really matter who you're talking to, because it is a phenomenon like 6 degrees of separation. At the same time, if the graph is disconnected, then we can win a lot by learning this graph first, and then either using greedy covering graph algorithm or looking at the clusters, we can win a lot by figuring out this graph first, and then giving the information to influential rumor mongers. How, in this case, it may be 2 and 1, for example. So just very briefly, of course, this is a very interesting problem, how to figure out this graph and so forth, and then algorithms, how to choose the people the influential rumor mongers. So I just very briefly wanted to show you that in this case, the matrices and graphs are used to represent users. Users that are looking at the web pages on the internet. So then the next project was the project about semantic graphs. Suppose a person is trying to find out suppose a person has the following task. I would like to go to a movie that is located somewhere where my friend lives nearby. So this is a complicated query, for example, to a database. At the same time, it can be represented by semantic graph. So this is another application of graphs. So in this case, the nodes of the graphs will represent the entities that are involved in the query, and then the links have notation that show relationship between these entities. So even such a complicated query can be very efficiently represented by a graph. Suppose you can have a person, so the entities are person, movie, location of the person's house, location of the movie, location of the person's friend's house, for example, and then the person. And then such a complicated query can be this is, by the way, was done it was used in a sidewalk application by Microsoft that shows what's going on in a city. And then using the graph, you can show the connections between those entities. Person is looking for a movie. Movie is playing at a certain location. Then there is relationship between locations, that this should be close to each other. And then there is a connection here that person lives at a certain location. So this is a very different application of a graph, for example, that shows how to give a complicated query. And then, for example, we can have once we represent information in the following way, there are so many things that we can do. Also, suppose also a person is looking for a theater. Then once you have this information, represented as a graph, there are a lot of interesting transformations of a graph that can be done, and this graph can be analyzed. It's called semantic graph. So for example, we can also know that movie, just separately, that movie, theater, and concert are all part of entertainment. Part of entertainment. Then, for example, suppose you are advertising a concert. Then, for example, one of the very important transformations that can be done to this graph is generalizing it. We can see that person is looking for a theater and a movie playing at a location. Then we can see from this that the person is actually maybe looking for entertainment that is just playing somewhere where his friend lives or her friend lives. And so in this case, we can see that we can generalize this graph. So this is one of the transformations on the graph. And replace theater and movie by entertainment. And then suppose you have an advertisement for a concert, then this would be very relevant to give such a person the advertisement for a concert, because it's also a part of the entertainment. So we did a lot of various work with this graph, clustering algorithms. Then, for example, we needed to define distance between such graphs. For example, if you would like a person to help to complete a task, then we would go to historic data, see what he or maybe the person's friends were making similar queries, and then we define the distance between these graphs, and then see what to help person to complete. So, for example, person just starts to write the query, and the program would finish it for the person. And so we did a lot of work on that. And for example, here it's very efficient. Once you represent it by a matrix, you can, for example, borrow Euclidean distance from it. So then it's very easy to define a distance between graphs once they're represented by vectors or matrices. We worked with a distance that was related we put all these graphs into a lattice, and with the transformations of generalizing or adding different entries. And then we would say that two graphs are similar if there is a short set of transformations that would lead from one graph to another. Or especially if there are big common subgraphs, then we would say that two graphs are close to each other. So this is a different application of graphs, also in matrices. And then I would like to show just one more application of graphs. Suppose and then I'll talk in more detail about the inverse problems for Gaussian Laplace operator. This will be more technical than this is just to give you an idea how graphs can be used. So suppose we are looking at the person looking at the internet web pages, and we would like to predict what would be the next page the person would look at, to forecast the usage. Then we could speed up this is called prefetch caching. So in this case, we could speed up the download of the pages, for example. So here we can use matrices in the following way. This is an example of collaboration of a person and the computer. So the project I was working on was the following. A person is looking at the patterns in the history of a person looking at the web pages. And then a person would make certain hypotheses about the patterns a person is looking at. So for example, patterns of the following way. If a person is looking for news on Monday, news internet pages on Monday, probably a person will look at on Tuesday also on the internet, on the news web pages, and Wednesday because they're working days. And maybe if a person is looking at the game pages on Saturday, then probably would look at game pages on Sunday also. So a person can make different hypothesis about the patterns that a user is, about the users looking at the internet. And then using that the program would take this hypothesis, check it against the historic data, and give the weights to each of the hypotheses. And then to combine them in order to produce the final forecast for what a person is going to do. So in this example, the predictions were made in a calendar-like fashion. So for example, Monday, Tuesday, Wednesday, Saturday, Sunday. And the way a person would make predictions is, suppose blue color corresponds to news. Then we can say that if a person is looking at the web pages on Monday, probably he would look at web pages on Tuesday. They can color it this way. And if looking at news web pages on Tuesday, probably will look at them on Wednesday also. They can also color it in blue, and so forth. And then for game pages, we can use, for example, a different color. This is for games, for example. And then the program would go look at the historic data and see when, maybe 5 days of the week, the person was looking at the news web pages, and then on the weekends, the person is looking at the green game web pages. So then the program, let's just have a printout, would, I'll just show you. So a person would make certain predictions of that kind, and then the program would go into historic data and see which of the predictions are more true and less true. And then it would give so the hypotheses have different colors here. And then all hypotheses are weighted to corresponding to their validity against the historic data. And then this can be used for predicting this is thick line corresponds to actual usage, and then the thin line corresponds to the forecast that is made. So if you would like, you can take a look at this. Because this is different. So this is one of the United States patents. So these are all projects I was working on in the Microsoft research. So now I would like to talk in more detail about more graph theoretical problem, and in much more detail. So what time have we started a little bit later, or?
That's fine. We have about 20 minutes or more.
40 minutes?
Oh,
30?
Yeah, 30 minutes.
30 minutes, okay. Yeah. So I'll talk in more detail about the inverse problems for planar graphs. So this is more graph theoretical kind of problems. So it's the following. And motivation from this problem is from non-intrusive testing. We are going to make a certain measurements on the boundary of the planar graph and try to find out properties of that graph. Or I will also talk about continuous case when it's a domain with weights. And the motivation is from medicine, where you would like to make maybe only measurements on the surface of the body and to figure out what is inside, and also from oil and gas production industry, where people are looking at electromagnetic fields and the boundary of the earth and try to find what is inside. But you can also see that this problem, very many problems in mathematics and in graph theory can be transferred to this. So here is the problem. Suppose we have a planar graph. The planar graph means that it can be drawn without self-intersections. Then the very important matrix that represents the planar graph is so-called Laplace matrix or adjacency matrix. So this is going to be the following matrix. If there is no connection between two vertices, then we put 0. So for example, 1 is not connected to 4 and 2. So there is going to be 0 here and 0 here. and 1 is connected to 3 and 5. And then we put minus conductivity. We can think of this graph also as an electrical network, for example. There are different models I can use. Let me talk about it as electrical network, for example. Then suppose we have conductivity here. Then we put a minus conductivity in the, if there is a link between two vertices. So this is symmetric matrix, for example. And then on diagonal, we put sum of the all conductivities. So gamma I1, for example, sum over of all conductivities. This is so-called Laplace matrix for a graph. So if the problem is the following, and is the following. Suppose we observe the pattern of potentials and currents of this graph at the boundary nodes. And boundary, for example, in this case can be 1, 2, 3, and 4. What can we say about the graph inside? And usually boundary is much smaller than the interior. So here I drew very little boundary nodes, but there can be a lot, for example. So this seems to be a difficult problem because interior is usually much larger than the boundary. What can be said about the graph from looking at potentials and currents on the boundary of the graph? Or equivalently observing the random walk. Suppose we look at the random walk on this graph. This also related. Here also, this random walk can be viewed as looking at the web pages, for example. But suppose we look at the particle entering the probability at which particles enter the graph, then go through the random walk according to the probabilities proportional to the conductivities, and we look at where they enter and exit. This is equivalent to looking at the potentials and currents on the boundary of this network. And I will write an explicit formula in a second. So what can be said about the graph? So, and then there is also a continuous analog of this problem. If you have a positive conductivity function, we can also apply potential at the boundary and look at the current. So all boundary measurements can be very efficiently put into this map. We apply potential at the boundary and we look what current results. So what's happening? When we apply a potential at the boundary, there is going to be potential inside. And this matrix allows very efficient, to write it very efficiently. So Kirchhoff's law Kirchhoff's and Ohm's law can be written very efficiently in this case. Suppose we put a certain potential at the boundary, then the potential inside, let's call it U, vector U. U sub I, potential. Then the fact that the Kirchhoff's law is satisfied at the node I can be written as mu i's coordinate equal to 0. The continuous analog here is the following. Also, if we apply potential F at the boundary, the continuous analog is the following. Gamma U sub x, gamma U sub y equal to 0. And this is a Laplace operator. And so this is where the name for the Laplace matrix is. So let me write it now in more explicit form. What is this? What is our data and what we are looking for? So we are looking for the graph for the links and also the conductivity. What we are going to measure, and we are going to measure potential and currents. All potential and currents can be recorded in the one matrix. And this is so-called Dirichlet-to-Neumann map. Dirichlet data is potential, Neumann data is current. So we can explicitly calculate Dirichlet-to-Neumann map that actually has all the boundary information that we are looking at in the following way. So let's partition the matrix M into blocks corresponding to boundary nodes and interior nodes. So this we can number, for example, boundary nodes first and then interior nodes second. then matrix M has a block structure, A, B, C, D. Suppose we apply potential U. Then there is a potential on the boundary. This is what we are applying. And then there is going to be potential inside. And due to the Kirchhoff's or Ohm's law, here we are going to get 0, and this is U. Because there is a Kirchhoff's law and the Ohm's law satisfied here. And we are going to get some current on the boundary. So Dirichlet-to-Neumann map that has all the information about heating probabilities of the random walk, or it's a map from potential to the current, is the map from F to G. And this is a linear map. We can explicitly calculate it. This matrix also called, it's called Dirichlet-to-Neumann map. Sometimes it's called response map, how the object responds to potential. Response. We can explicitly calculate it in discrete case. So let's make a little calculation. What this block structure tells us that AF plus BX equals G, and CF plus DX equal to 0. So we can solve for X. X is D inverse CF. And then we can just see that G equals to A minus B D inverse CF. So this is the lambda, Dirichlet-to-Neumann map. And this is true also in continuous case, that this is a map from potentials to a current is a linear map. And so it can be written as F of theta, if we parameterize the boundary, equals integral over the boundary, sorry, G of theta equals integral over the boundary So in continuous case, the Dirichlet-to-Neumann map is represented by a function of two variables. That is a kernel, and this is continuous version of a matrix. So when we are working with a huge graph with small links, then the more efficient, then the model becomes continuous. And this is very important for scalability questions, for example. So given this, so this is the project I would like to talk in more detail now, is the following. It's a connection between continuous and discrete model, and what can be said about the graph from this matrix. And this matrix has all the information about what you can say about the graph, not without intrusion, only on the boundary, because this is all the measurements here can be made only from the boundary, and we are trying to find what is inside. So how to find out what can be said about the graph? Well, first, maybe you have seen this form somewhere before. This is in general true. If you are looking for the inverse of the matrix, and the matrix has the block form, then the block in the inverse has the same similar form. So in general, suppose you have a matrix A, B, C, D. We look at its inverse, X, Y, Z, W. So the inverse means that this is identity, 0, 0. Then one can solve this in the one can solve this system of equations with blocks of the matrix Cx. Z equals minus D inverse C, and then X equals A minus B D inverse C inverse. So this is another way to look at the Dirichlet-to-Neumann map. It's if this is a matrix M, then this is inverse of this matrix. So this matrix that has all the information about the random walk at the boundary and potential to current map has its block is its is a block in the inverse of the Laplace matrix. So what can be said about the graph? Well, we need one more identity. This is called Schur complement of the matrix. The Schur complement of the matrix with respect to block D. This is called Schur complement, and it's sometimes written as M Schur complement D. So, and there is identity that connects the determinants in the Schur complement. It's the following one. Suppose we look at the matrix A, B, C, D. I will prove it and write at the same time. D inverse 0. Then here you get exactly the Schur complement. So this is an obvious identity, and what it tells us, here is the Schur complement, this is a Dirichlet-to-Neumann map, this is the Laplace matrix, and so this, since it's a diagonal operator, then determinant of this matrix is just 1 over determinant of D, so we can see the determinant of M divided by determinant of D, and this is also identity, so determinant of this matrix is exactly determinant of lambda, and this is true for any entry or a block. So once we know Dirichlet-to-Neumann map, we know ratios of determinants in the Laplace matrix. And so what it tells us, this gives the first connection between the matrix. So we have two different representations of the graph, as a graph and as a matrix. And this gives the first important connection between the graph and the matrix, is that if we know Dirichlet-to-Neumann map, we know determinants of blocks in the Laplace matrix. Now, this can be to what graph theoretical information can this be transferred? It turns out then that what is the determinant of a block in the matrix? It's a sum of a product of terms. And how these terms are constructed? We take one entry from each column and each row. This is how determinant works. And so if you know a determinant in a Laplace matrix, what can we say about the graph? Turns out that we can look at the non-zero terms in the expansion for the determinant. So we can take matrix lambda, look at certain set of rows and columns. These are just rows, for example, and columns. And this has to be equal, this is just always the same. So this is going to be equal to sum of products. And these products are certain gamma ij's with certain weights. And turns out that if we can actually trace every non-zero term in the determinant into a path in the graph. And this is where you can see the random walk interpretation is also very, very convenient. So suppose we have a non-zero term. Since we can just read from it the conductivities that are not zero, and if every non-zero term is going to give us a disjoint path in the graph. Because disjoint, because we exactly take always one entry from each row and from each column. So this is going to be a sum over disjoint paths from P to Q. So here is a small example. Suppose we have the following graph, just very small graph. If you look at its Dirichlet-to-Neumann map, the determinant, if we take columns 1, 2, and rows 3, 4, determinant is going to be 0, because there is no way to connect disjointly 1, 2, and 3, 4. If we look at the Dirichlet-to-Neumann matrix and we look at rows 2, 3 and columns 1, 4, then it will be non-zero because there is a disjoint path. So this is the first step in solving this so-called inverse problem. And usually forward problems are problems of solving equation. And inverse problems are problems of finding equation from its solution. So here the forward problem is finding the matrix from the graph, Dirichlet-to-Neumann map. And then the inverse problem is finding the graph from the Dirichlet-to-Neumann map. So what we can see then that if we know Dirichlet-to-Neumann map, we know all disjoint connections in the graph. Well, there are certain transformations of a graph, and these are transformations very similar to Radermeister moves in the knot theory, and also this is transformation known as Y delta for transformation in electrical engineering, that do not change the connections in the graph, disjoint connections in the graph. And these are the following transformations. Whenever in the graph we see the following pattern, whenever in the graph we have a vertex of valency 3, we can replace it by a delta. So this is like y replaced by a delta. And the weights should be recalculated in the following way. If these were A, B, and C conductivities, then the new conductivities are AB divided by A plus B plus C. And here is going to be CB divided by A plus B plus C plus C. And here is AC, A plus B plus C. So this transformation, that it's very easy to see, that does not change disjoint connection of in the graph. If there was disjoint connection between boundary nodes, it still will be there. It's a very simple check. So this transformation cannot be seen from the Dirichlet-to-Neumann map. And then there are other transformations that can be obtained actually from this one by setting ABC to 0 or infinity. Suppose we have somewhere AB, then we can replace it by one conductor, A plus B. Suppose we have two conductors in series, then we can replace it by one conductor. Suppose we have just a conductor of, that is connected to only one node, then it can be ignored. And the last one is, suppose you have a closed conductor, then this also can be removed. So this is the first result. It turns out to be the following, that if you know Dirichlet-to-Neumann map of a planar graph, then we cannot find the graph up to these transformations. So first of the results is actually this is an exact result. If you have two graphs that have the same Dirichlet-to-Neumann map, then they can be one can be transformed into another by a sequence of these transformations. So graph can be found from Dirichlet-to-Neumann map up modulo these transformations. I will show you a little bit idea how this can be proved. And answer there are other questions to ask. Suppose we know the graph, can we find the conductivities? So here we assume that we do not know neither the graph nor conductivities. Suppose we know the graph, can we find conductivities? So to answer this question, there is a very important to give a planar graph in the following way, using its so-called medial graph. So I drew graph here as limbs and edges, but one can introduce a medial graph of a planar graph. It's the following. Suppose we are looking at set of curves on the plane. Suppose we just have set of curves on the plane. Then this always divide the plane into regions that can be colored in a chessboard-like fashion. So we can color this. Maybe I use a black, so then it's more chess-like. And then whenever we have set of arrangement of curves, they divide the plane into regions. And then we can construct a planar graph from it by putting a node in every, for example, black region, and then connecting the nodes if there is a common point between the regions. This way we can obtain the graph from arrangement of curves, and we actually get two graphs, the graph and its dual. And dual graph would correspond to a different choice. If we chose white regions to be our points, so then we have a graph and its dual. Dual graph means that every edge is orthogonal to an edge of the original graph. So it turns out that every planar graph has a medial graph associated to it, and these transformations look much simpler for the medial graph. The transformations look in the following way. So if you are making Y delta transformations and this transformation from electrical engineering, then the medial graph changes in the following way. Whenever we have a loop like this, it can be removed. Whenever we have a lens like this, it can be removed also. And then Y delta transformation is the following. Suppose we have a region looking like this, then we can move this above and get this transformation. So these moves, they resemble the moves, Radermeister moves in the knot theory. By these transformations, any arrangement of curves can be changed into arrangement of pseudolines. And pseudolines are curves that are curves, at the same time they behave like lines in the following way. They have no null self-intersections, and they do not intersect more than once. And there are no closed curves. So it turns out this notion gives an answer to the second question. Suppose we know the graph and we would like to find out conductivities from the Dirichlet-to-Neumann map. Then conductivities can be found uniquely if and only if the corresponding medial graph is arrangement of pseudolines. So in this case, if we know the medial graph, then we know the graph, and Dirichlet-to-Neumann maps gives us conductivities. And this also gives an algorithm how to figure out the graph itself. So there is an identity connecting the arrangement of pseudolines with the disjoint connections. Basically, when we have arrangement of pseudolines, then we can look at how far these are called geodesics, the curves in the arrangement of curves. We can see how far they go inside the graph. And if they return quickly, it means that there is no disjoint connection. So it's not very difficult to find out the order in which the geodesics in the pseudoline arrangements live and exit the graph from disjoint connections. And by the way, I should say this is a collaborative work with Professor Curtis Morrow from University of Washington and with RAU program, RAU summer school program on the inverse problems. So the graph then can be figured out in the following way. This also gives an algorithm for finding the graph from the Dirichlet-to-Neumann map. So if we know Dirichlet-to-Neumann map, we can find disjoint connections in the graph. From disjoint connections, we can find the returning geodesics. So the order in which they enter and exit. From this, we can figure out the arrangement of pseudolines. And from pseudoline arrangements, we can figure out the geodesics by Y-delta transformations. And from this, we know the medial graph. And from that, we can find the graph itself. So this is the line. So then there is an important question. Given a matrix, is it a Dirichlet-to-Neumann map? Classification. What are possible matrices that arise in this fashion from planar graphs? And turns out that the answer is also can be given in terms of determinants. Whenever so a matrix is a Dirichlet-to-Neumann map of a planar graph if it's symmetric, has some of the rows and columns 0, because if you apply potential 1, there is no current flowing, so this matrix times constant vector has to be 0. And then all determinants have to have particular sign, depending only on its size. So whenever we have a matrix that has the following sign of the determinants in it, then we can always construct a graph. Then we can always construct the graph this matrix will be Dirichlet-to-Neumann map. So we can completely classify the data. What are possible observations that can be made? The matrix is valid only if it has all determinants from P and Q do not interlace here. Do not interlace. The same thing is true, and this is collaborative work with Professor Morrow from University of Washington, is for continuous case. It turns out that the same property is true for the function of two variables that represents Dirichlet-to-Neumann map in the continuous case. And therefore, one can take the continuous Dirichlet-to-Neumann map, look at its restriction, and construct a graph to generate a grid so that its Dirichlet-to-Neumann map is going to be exactly the same determinant. If it's lambda or k, it's also going to be true. So what it tells us that restrictions of continuous Dirichlet-to-Neumann maps are discrete Dirichlet-to-Neumann maps. So this suggests a way how to construct graphs whose Dirichlet-to-Neumann maps approximate the continuous ones. So for example, this tells us how to connect discrete and continuous problems. So how much time do I have more?
We need to wrap up because you said you'll have lunch and the rest of the activity.
Okay, so just one more thing I would like to say is there are. Do I have 5 minutes here? Okay, so here is one more amazing fact I just would like to mention. there is an example of a Dirichlet-to-Neumann map in the case conductivity equal to 1. Then the Dirichlet-to-Neumann map can be explicitly calculated, because if you apply potential F sine alpha k, then the corresponding potential inside U is going to be R to the k sine alpha k. And then if you look at the current, its derivative of this function, this is going to be k sine alpha k. So in this case, it's very easy to write the spectral decomposition and of the Dirichlet-to-Neumann map. And this is a complicated map. Its eigenfunctions are sines and cosines, and eigenvalues are k, the frequencies. What turns out that what is the very amazing fact that was noticed by Professor Ullman from University of Washington is the following: that if you look at lambda squared, even though lambda is very complicated non-local operator, if you change a little bit f somewhere on the boundary, the G current is going to be changed everywhere. If you look at its square, it turns out to be k squared sine alpha k. So this is just simply minus second derivative of the function. So this is an amazing fact. This is an amazing fact that such a complicated operator has a very simple square. And to understand the connection between the continuous and discrete case, and this is collaborative work with Vladimir Druskin from Schlumberger and Sergei Shvadurov from Schlumberger and Shari Moscow from University of Florida and Leonid Ingerman from Central Geological Expedition in Moscow, is that we were working on connection between discrete and continuous case. It is possible to construct discrete graph that has the same property, that its Dirichlet-to-Neumann map is a complicated object. At the same time, its square is a simple matrix of second differences, 2 minus 1. So there is a discrete notion. And I have constructed two such graphs just recently, just several weeks ago, one infinite graph and one finite graph. It just showed that different kind of connection between continuous and discrete case. That this one thing is just to look at the approximations, how they differ. At the same time, is to check if such a phenomenon is true in discrete case. And just to finish, I wanted to say more about the continued fractions. So I'll just, I don't have time. To understand the connection between continuous and discrete case, it turns out to be very important to look at continued fraction expansions of functions. And I'll just say one fact. For example, golden ratio is an example of a number that has a very nice continued fraction. So I don't have time to stay in more detail, but just in general, the continued fraction of a number is expression like this, where a are integers. And for example, all numbers have exactly one continued fraction expansions. If they are rational, then the continued fraction is finite. If you look at the restriction of several floors in the expansion, then this gives optimal approximations and optimal rational approximation of a number. And if a number is quadratic number, then continued fraction is periodic. It's different as with decimal expansions of numbers, where if a number is rational, then it's periodic. Here, if it's quadratic number, it's periodic. And so it turns out that the connection between discrete and continuous model is very similar to the connection between number and its continued fraction expansions. I don't have time to say in more detail. I'll just prove this identity, why it's true. If we call this x, then what's happening, if we take 1 divided by x and add 1, then we get x again. Right? So, and therefore, x has to satisfy a quadratic equation.
Sorry, guys, I think we have just one.
Okay.
Sorry to interrupt you.
So these give exponentially fast approximations, and this allowed us to construct grids that give exponentially fast approximations of discrete model onto continuous ones. Thank you very much for your attention.